thank you very much for your for the committee to. So I have to. I'm very glad to have the chance to introduce our work, optimal design and operation of reverse osmosis seawater desalination system with boron removal. Here is the outline of the my presentation, and let's begin with a brief introduction. And now, boron removal is requested during the design and operation of seawater oil plants for drinking and agricultural irrigation application. The oil system should be optimized to meet the daily variation of operation conditions, and we also need to consider the economic, energy, and the environmental issues of the system. So the main concept of the current work is, first, we build our network. It includes the pumps, energy recovery, our unit, water tank, and the stream links. And we control the number of operating pressure vessels. We choose the best water tank volume, and we control the permeate splint ratio and the pitch of the feed. And we also took energy-based XQ environmental analysis. So if we give a time of variation of water demand, temperature, electricity price, so we can get the best system design and the operation conditions and sort on the bound restricts. The part 2 is a process model. We use irreversible thermodynamic mode to describe the transport phenomena inside the pressure vessel. The water flux and the bound flux was described in these equations. And the temperature effect on the system include the water, salt permeability, and the bond permeability, and the mass transfer coefficient was fitting in the model, and the seawater parameters properties are also included, but the temperature effect on the efficiency of the pumps and the pressure exchanger was not included because neglected change during the operation. And we validated the model with the IMS design from hydronautics, and we found it has good accuracy. When the pH treatment is ignored, the dynamic behavior of the water level, salinity, and boron concentration in the water tank can be calculated based on its following differential equations. And the operation condition of the pumps changed during the during time. So we calculate the pump head and the power consumption at standard frequency, and if we change the frequency, it will lead to the following change, and we can calculate the efficiency of the pumps, and the efficiency of the frequency conversion motor will be calculated based on the following fitting equation. And we built the economic model, and the total analyzed cost is the sum of capital cost and the operation cost. And it should be noted that the number of pressure vessels and operation conditions are changed. So we calculate the capital cost based on their highest value during 24 hours. And we also built the energy-based X-scale environmental model, the MD concept suggested by Adam can qualify the environmental impact and eco-efficiency of a system. The methodology used transform the energy, material, and the monetary of the momentary flows into a solar energy joules, so we can evaluate the system and the same scale. The energy rate of the ice stream in the system is a product of specific energy rate and the X-ray rate or work rate. So the environmental balance for the equipment can be obtained, and the equipment related energy rate is the sum of construction and maintenance. So we can calculate the overall performance using this equation. So finally the problem can be built to a mixed integer differential algebraic optimization problem. It includes Sperron model, network model, storage tank model, cost model, and X-scale environment model under the system flow constraints and the initial and the final conditions. Part 3 is the solution strategy. The hybrid discretization method for differential equations is used, and the solver simple branch and bound and the games is used to solve this problem, and about 2 or 3 hours is requested to solve the model with a lot of equations and variables. And the solution of the model without daily variation could give a better initial points. So the part 4 is results and discussion. A two-pass network with film-time memories are studied here, and figure 3 showed the variation of freshwater demand and temperature, electricity price. First, we calculate the effect of area of water tank and the constant temperature and the electricity price. We can see that if we increase the water tank, the annual operation cost and the fixed charge are also decreased, and the best site is 210 square meters. So we can go through the profiles of the optimal control and status variables during the operation. We can see that if we use a large water tank, the number of pressure vessels, recovery rate, feed flow rate, and the pressure will be nearly constant. So it's easy operation model, and we can adjust the spindle ratio, pitch, or the pump conditions to meet the water and boron restrict. And part 2 is the effect of memory type. We compared 3 types of sequential memory and 2 types of package memory, and we found that the high-flux seawater membrane and high rejection brackish water membrane show the lowest water cost and energy consumption. And this configuration has the lowest number of pressure vessel and low pitch feed, so the water cost can be saved. and this we compare the effect of bond concentration of the product. We found that we can control the spin ratio and pH value, so we can adjust the product concentration. And finally, we compare the different objective function with the penalty of average rate of product. We found that the operation conditions with annual operation cost fluctuate in a very large range, such as the number of pressure and the pressure vessel and the feed flux. Here is a figure of the extreme destruction breakdown for during this time for the case with the objective of total analysis cost. We found that less number of operating pressure vessels and the feed flow rate of seawater result in the low actual destruction at 2 a.m. And we also compare the different variation trend of the emergency rate of the product. We found that the overall performances are decreased with the increase of the penalty function, and but the environmental impact on product is decreased significantly. And we also compare the cost and the emergency rate of the product for the 6 cases, and we found that the objective of total analyst cost and the sum of emergency rate of product could give the best cost and emergency rate performances. So finally, we could draw the following conclusions. A nearly constant pressure and flow rate, feed flow rate are achieved with larger water tank. We find the best membrane type, and we can control the spin ratio and pH value to control the bond concentration. And finally, for the case with temperature and the electricity price fluctuation, the solution with the objective total analysis cost and the penalty function of emergency rate will keep a balance for the water cost, energy consumption, and the environmental impact. Here is the acknowledgement. Thank you very much for your time and attention. Thank you.
Thank you very much for the very nice talk. We have one quick question. You mentioned about that membrane, the type of membrane will play a role in the energy cost, in the energy consumption. But how about the water quality, the product water quality? Does that have some kind of a trade-off when you go down in energy consumption? Is it going to adversely affect the water quality?
Yeah, we set upper bound for the salt concentration of the product in the model. So it's under the upper bound during the operation. So it's not a problem.
Okay, that's very good. Thank you so much.
Thank you very much.
So we will move on with the session because of the time constraint. Now, I will hand the session over to Dr. Wang, who will basically chair the rest of the session. So he will introduce the next 2 speakers. Dr. Wang.
Okay, thank you, Professor Tang and Dr. Du. Now let's introduce the next speaker, Hui Zhao, from East China University of Science and Technology. His topic is about the degradation of polyimide nanomembranes by bromide, changes of chemical properties and filtration performance. Welcome, 会会长.
Okay, thank you. Morning, Dr. Wang. Morning, Professor Tang. My name is Zhao Hui. I'm a PhD candidate in East China University of Science and Technology. My topic is the degradation of polyamide membranes by bromine, changes of physiochemical properties, and filtration performance. There are 3 parts in my report today. The first is about the research background. I will introduce some basic information about membrane technology. The membrane technology has widely applied in wastewater treatment due to its high efficiency, low energy consumption, and higher selectivity. And according to the field distribution of membrane industry in China, we found that the membrane technology was most used in industrial water treatment, accounting for nearly 55%. And the output value increased from 30.7 billion to 16.3 billion yuan from 2010 and to 2020. And the polyamide thin composite membrane and a TFC membrane has most use in membrane technology due to their excellent permeability and selectivity. And we all know we usually add some disinfectant in membrane system to prevent the biofouling, but the weak resistance of the PA materials to oxidizing agents like the chlorine, bromine, or the hydrogen dioxide will reduce the membrane lifespan. But if we use a pre-disinfection step to remove the residue, this may cause the treatment cost increase. And still now, there is not a consensus agreement on the degradation mechanism when membrane exposed to chlorine. The common degradation mechanism include amide chlorination, chlorination promoted hydrolysis, the ring chlorination, the depolymerization, and the loss of hydrogen bonding site. The chlorine is the most used disinfection in the water treatment, and it affected by various factors, such as the type of disinfectant, the exposure intensity, and the substrate background of water quality. Compared to chlorine-based disinfectant, the bromine-based disinfectant has lower toxicity, higher chemical stability, and reactivity. Also has more effective sterilization. The bromine-based disinfectant often used in industrial wastewater, in spa and swimming pool water treatment. And compared with chlorine, the bromine has weaker electronegativity, the larger atomic radius, and higher halogenation reactivity. And this potential difference in bromine and chlorine might result in some opposite or different reaction pathway when membrane exposed to a disinfectant environment. So in this study, we used 2 commercial PA membranes, NF90 fully aromatic polyamide membrane and NF270 a semi-aromatic polyamide membrane to investigate the underlying mechanism of membrane degradation by disinfectant. Also, we want to identify the internal relationship between macroscopic properties and the microstructure of membrane in disinfection environment. And finally, we compare the induced membrane degradation effect between chlorine and bromine. Here comes to the result and the discussion part. And first, from the ACM and AFM analysis, we found the NF90 had a rough surface with a ridge and valley structure. And after exposed to bromine, the membrane surface become more compact. And after exposed to bromine solutions, the NF270, this membrane, some cracks are observed on its surface. And according to the roughness, the membrane become more, the membrane roughness increased when it exposed to bromine solutions. And for NF270, there is not a significant difference because the NF270 the structure was more stable than the NF90. And from the XPS spectrum, the bromine peaks were reviewed at 3 binding energies for brominated NF90 membranes, while such peaks were not obviously observed for the virgin one. And the bromine content increased dramatically from 0.2% to 44.5% for NF90 exposed under 10 ppm bromine. And the further decrease in bromine content concentration up to 500 bromine only resulted in bromine content of 7%. And the bromine content for virgin and brominated NF270 didn't show a significant difference. The ratio between oxygen to nitrogen increased from 1.2 to for virgin NF90 to 1.5 for membranes treated by 10 ppm bromine. Then the ratio kept nearly constant. And the ratio between oxygen to nitrogen for virgin and brominated NF270 was nearly constant at 1.4 due to the stability of the tertiary amine nitrogen. And the FTIR results show that the peak of amide 1 bond shifted to a higher rate number after exposed to bromine. And the breakage of hydrogen bonds between carbon and amino groups and the addition of carboxylic groups formation may contribute to this shift. And the disappearance of amide 2 bond and aromatic amide bond may suggest that the hydrogen on amide groups and aromatic rings may be replaced by bromine by electrophilic substitution. And the FTI spectra for NF270 didn't show a significant difference. As for the contact angles, the contact angle for NF90 increased significantly after the membrane was exposed in bromine solutions, which implies a reduced hydrophilicity for membrane surface. The increased hydrophobicity for PA membrane surface was a result of competing effect between the incorporation of bromine, the increased number in carboxylic groups, and the increasing surface roughness. The NF90 became more negatively charged after it was exposed to bromine solutions, which is mainly attributed to the bromination promoted hydrolysis, that is the increase in carboxylic groups. The minor increase in charge density for NF270 might be a result of the decreased content of amino groups induced by bromine substitution. And the membrane effective pore radius, the effective pore radius for NF90 decreased from 0.31 nanometer to 0.29 nanometers. And for NF270, it was decreased from 0.40 to 0.39 nanometers. The competing effect of the hydrolysis promoted pore opening, and the steric hindrance induced pore blocking might responsible for the effective pore radius variation. As for the membrane changes, membrane performance changes, the permeability was decreased by 64% after the membrane was exposed to 10 ppm bromine, and a further 18% was observed when the membrane exposed to the 500 ppm. And the significant decrease was attributed to the decrease in the decreased hydrophilicity and decreased pore radius. And the minor decrease was only because of the decrease because the decrease in the membrane surface hydrophilicity. As for the charged solute permeability, it was decreased by 90% when it exposed to 10 ppm bromine and only 2% to under 500 ppm bromine. The significant decrease was resulting from the significant decrease pore radius and increase in surface charge, resulted in the enhanced charge repulsion. And the minor decrease resulted from the minor change in pore radius and charge. The neutral solute permeability was decreased by over 20% under 10 ppm bromine and about 1% to 9% decrease for further decrease to further exposure to 500 ppm. And similar to that in pure water permeability at charged solute permeability. The significant decrease was resulting from the decrease in hydrophilicity and pore radius, and further minor decrease resulting from the decrease in hydrophilicity. The chlorination and chlorination promoted hydrolysis are the common proposed mechanism for PA membranes exposed to chlorine. And in this study, the bromine incorporation, the shift, and the disappearance of characteristic bonds, and the increased ratio between oxygen to nitrogen and the increased number of carboxylic groups indicates that the degradation mechanism of unbromination and bromination promoted hydrolysis under minor bromine exposure conditions, and further ring bromination was occurred under severe bromine exposure conditions. The bromine and chlorine are two most dominant oxidizing agents for biofouling control and water disinfection. The bromine has a higher reactivity than chlorine, which can be more prone to incorporate into the membrane surface. And the more hydrophobic of bromine than chlorine might cause a more hydrophobic membrane surface. It is worth noting that the bromination and chlorination resulted in opposite variation chains for water permeability and neutral permeability. The increased water permeability and decreased surrogate rejection after chlorination might attribute to the reduced cross-linking degree. By contrast, the weakened water permeability and solute permeability might be attributed to the synergistic effect of reduced hydrophilicity and reduced effective pore radius. Here comes to the conclusion part. This study investigates the effect of bromine on physiochemical properties and filtration performance of PA membranes. For fully aromatic polymer membrane NF9O exposed under a mild bromine condition, that is the 10 ppm bromine, the bromine incorporation resulted in more negatively charged and hydrophobic surface and narrower pore channels. The permeabilities of water and neutral solutes were reduced by 64% and 69% to 87% respectively. And the further exposure, 100 and 500 ppm bromine, resulted in a more hydrophobic surface and a minor further reduction for water and solute permeabilities. Compared with chlorine, the different incorporation efficiency and properties, like the atomic size and the hydrophilicity of bromine, resulted in opposite chains and/or different degrees for the variation of physiochemical properties and filtration performance of membranes. And finally, the fundamental understanding of membrane degradation by different oxidizing agent is essential for simplifying membrane-based wastewater and seawater treatment process. the proper selection of disinfectants or cleaning agents, and the fabrication of oxidant-resistant membrane materials. At this part, this math has been published in Environmental Science and Technology. And that's all. Thank you for your attention. Any questions and suggestions, please?
Hello. Seems that I do not see Dr. Wang here. Oh, he's back. He's back.
Oh, sorry, it's my mistake. There are some error in the Zoom. So
Don't worry, don't worry. So now it's a Q&A session. I saw one question from Men Jia. So the question was, what agents are used for traditional degradation, and will the use of bromine as degradation reagents increase the risk of operation?
Okay. The chlorine, we have to acknowledge the chlorine is the most commonly used disinfection reagent in now's wastewater treatment. But the chlorine has also been used in some typical water conditions like the industrial water, the swimming pool water, and the spa water. And this bromination disinfection is also used common in the seawater desalination. That is a chlorination with bromide ions. The bromide ions can be oxidized to form the hyperbromic acid, and that is the that also is the common bromination disinfection. And as for the risk of operation, increase the risk of operation. Let me see. Since the chlorine and bromine are two reagents, they both have the high oxidability, and the risk of operation, both they have the risk of operation when they used in the disinfection. But as we referred in my report, the bromine reagents have higher reactivity than chlorine. Then when we use the bromine as the disinfection reagent, we can consider to use little in the quantity. We can
so I guess anyway, in real application, you probably don't have a choice because, for example, in seawater, you do have bromides there.
Yes. Thank you, Professor Tang.
Yeah, well, anyway, produce this kind of a bromine species.
Yes.
Yeah, thank you very much for the nice presentation. So because of the time constraint, we have to move on. So we'll ask Dr. Wang to introduce the next speaker. Dr. Wang.
Okay, thanks, Professor Tang, and thanks, Dr. Zhao. Next speaker is Ki-ho Park from Chongnam National University, Republic of Korea. His title is a theoretical investigation of and critical comparison of energy consumption, actual application, and irreversible energy loss in batch, semi-batch, and continuous RO system. Let's welcome Park.
Thank you, Dr. Wang. And can you see my screen?
Yes.
Yeah, okay, thank you. And so glad to see you in this even at the virtual conference. And my name is Kiho Park, an assistant professor at Cheonnam National University in South Korea. And so today my presentation topic is regarding the theoretical investigation and critical comparison of energy consumption, actual application, and irreversible energy loss, batch, semi-batch, and continuous RO systems. So this is the table of contents. I will start with the introduction. And so maybe in the current hottest issue in the desalination topic is about the energy and environment. So about the energy consumptions, and definitely the SWR or seawater reverse osmosis is the most popular technology because of its lower energy consumptions. So we have to think about the energy consuming unit in SWR process to improve the energy efficiency of the SWR plant further. So in the energy consuming unit, SWRO, maybe the high pressure pump and booster pump and any other pre-treatment and post-treatment, maybe the energy consuming unit. So we have to think about how to reduce the energy consumption in these energy consuming units. So we can see the current energy consumptions in each unit. For example, the pre-treatment and post-treatment also consume the energy consumptions. However, the most energy consuming unit is definitely the SWRO unit itself. So maybe the energy consumption in current level is about 2 to 5 kilowatt hour per cubic meter for seawater desalination. So this is a recent trend of energy consumption in SWRO plant. So supported by membrane technology development, the SEC of SWRO has been reduced in recent decades. So due to the low energy consumption, so many SWRO plants has been installed in various spots. So the capacity of SWRO plant has been extended tremendously. However, as you can see that the SEC of SWRO looks quite to be saturated, and compared to the theoretical minimum energy, there is still room of effort to reduce the energy consumption further. So if the SEC of SWRO could be reduced further than the current state, then the impact of reducing SEC would be very tremendous because of you can see in this plant capacity, it's very tremendous. So to reduce the energy consumption further, we have to think about the current energy consumption in the SWRO systems. So this is the simulation result and then breakdown data about the energy consumption, and compared to the theoretical minimum energy, the current energy consumption is 2.26 kilowatt hour per cubic meter, and the additional energy consumption compared to the theoretical minimum energy is about 1.19 kilowatt hour per cubic meter. So there's a room of effort to reduce the energy consumption, and as you can see in this data, you can identify that irreversibility is the highest portion of the energy consumption, additional energy consumption. So we have to think about how to reduce the irreversibility in the SWRO systems. So about the irreversibility in the pressurization step, various researchers have discussed about how to reduce the irreversibility in the continuous RO systems. Actually, in the continuous RO system, the irreversibility is origin by instantaneous pressurization steps. So if we split the pressurization step into like this manner, then we can reduce the energy consumptions by minimizing the irreversibility, even though we have to think about the additional installation cost or the operational issue in this kind of two-stage RO configurations, then anyway, we can reduce the energy consumption by reducing the irreversibility. So we can think about the further configuration by increasing the stage of the splitting pressurization step, and theoretically, infinite staged RO configuration is regarded as a batch RO configuration. So the batch RO configuration can be said to be the nice configuration for minimization of irreversibility. So this is the rationale of utilization of batch type RO configurations. And definitely this is the theoretical minimum energy consumptions. And compared to the single stage continuous RO systems, this is the exergy loss due to irreversibility. So by employing different RO configurations, for example, two-stage RO system and semi-batch RO system, batch RO system, then the irreversibility can be reduced compared to the single-stage RO systems. So as you can see, the semi-batch RO system and two-stage RO system can be effective to reduce the irreversibility compared to the single-stage RO system. And ideally, batch RO system has the lowest energy consumption by supported to minimization of irreversibility. However, the actual implementation of ideal batch RO is quite hard, so modified batch RO system in the current state is quite higher than the energy consumption of the ideal batch RO configuration. So we have to think about how to improve the batch RO configuration and then how to realize the ideal batch RO configuration to going forward for minimization of irreversibility. So this is in this study, we discuss about the various RO configurations. For example, continuous RO single stage step and multi-stage continuous RO step and batch RO configurations, semi-batch RO, usually called closed circuit desalination, and hybrid batch RO, which was developed by our group at first. And this is like a hybridization of semi-batch and batch RO configurations. So in the ideal energy analysis result, in batch RO, semi-batch RO, and continuous RO system, the ideal analysis results show that the batch RO has the lowest energy consumptions and continuous RO has the highest energy consumption. So in different research also have the same result. And the batch RO energy consumption has the lowest because this area, the area below each line is denote the energy consumptions. So definitely, in theoretically, batch RO has the lowest energy consumption. However, this is only obtained by ideal energy analysis, and we have the ideal energy analysis is helpful to understand the Bayesian mechanism and the effect of each RO configurations. However, we have to think about the practical energy consumption, so we have to consider non-ideal factors should be to analyze the energy consumption in each RO configuration rigorously. So this is the practical energy analysis result compared to the batch RO system and continuous RO system. So we fixed the same average permeate flux in each RO module for fair comparison. And as you can see, the batch RO configuration, and then this is the two-stage RO configuration, and the flux imbalance in each RO module can be reduced significantly in batch RO configuration. However, considering all of the non-ideal factors and in batch RO system and continuous RO system, the current energy consumption actually denoted by the area in below each line, compared to the osmotic pressure, this is definitely the theoretical minimum energy, and the batch RO system, the current actual batch arrow energy consumption is quite higher because of the increased pressure due to non-ideal factors. And compared to the two-stage arrow configurations, the energy consumption is quite comparable in batch arrow system and continuous arrow system. So to obtain low energy consumption in batch arrow system, we have to think about how to reduce the non-ideal factors in origin in batch arrow system, and how can reduce the non-ideal factors. This is the energy analysis and breakdown data in the batch arrow system. And so in batch arrow system is operating in two phases, the first pressurization phase and purge and refill phase. So energy consumption is arising in each phases. And so the results show that at recovery at the 80% recovery and 3 grams per liter feed concentration in brackish-water desalination, then the optimized design using the optimized design, the energy consumption is approximately 0.39 kilowatt-hour per cubic meter. This is the simulation conditions, and this is the breakdown data. And the below the white area is the osmotic pressure. So this is definitely the theoretical minimum energy. And this area is obtained by the non-ideal factors, so we can elucidate quantify the effect of the non-ideal factors, and then we can identify which direction we have to go forward to reduce the energy consumption by the non-ideal factors. So this is our future directions to minimize in each non-ideal factor. So the result can improve the energy consumption of the batch arrow system in future. Then this is a new concept of the hybrid batch arrow system. It is quite similar to operating a hybrid car. So at first it is operated as a semi-batch arrow phase, and they can be switched to the batch arrow phases. So it is operated at first hybrid batch arrow, the semi-batch arrow mode, and then next it is operated as a batch arrow mode. So this is the rationale of utilization of hybrid batch arrow systems, and the below area is the energy consumption. And definitely you can see that high semi-batch arrow has the highest energy consumption in these configurations, and batch arrow system has the lowest. And compared to the hybrid batch arrow system and the batch arrow system, the hybrid batch arrow system a little bit higher energy consumption than the batch arrow system. This is a small energy penalty. However, it can have another advantages by utilizing the hybrid batch arrow system. This is the ideal and practical energy analysis. And as you can see, this is the ideal energy analysis, and energy penalties arising by employing the hybrid batch arrow system. However, the size of the work exchange vessel can be significantly reduced by employing the hybrid batch arrow system. As you can see, the batch arrow system should have the work exchange vessel maybe 0.09 cubic meter. However, in the hybrid batch arrow system, the work exchange vessel is needed to have the 0.04 cubic meter, which is less than a half of the batch arrow system. So the hybrid batch arrow system can reduce the size of a work exchange vessel significantly, but very small energy penalty. And so considering all of the non-ideal factors, this is the practical energy analysis, and compared to the semi-batch arrow system, batch arrow system and hybrid batch arrow system has definitely lower energy consumptions, and the hybrid batch arrow system has only a small energy penalty. And at high recovery desalination, over 90%, then the additional SAC in purge and refill phase can be minimized by reducing the size of the work exchange vessel. Then the hybrid batch arrow system has a lower energy consumption than batch arrow system in practical analysis. So over 90% recovery, for example, the minimum liquid discharge or zero liquid discharge system, then hybrid batch arrow system can be a very competitive solution to in terms of the energy consumption rather than the batch arrow system. So the advantage becomes significant at increasing recovery. This is the ongoing research for the batch arrow system. So we are installing the viral scale system. So using and for validation of the batch arrow system, and we are making the optimization of energy consumption depending on the recovery and any other operating conditions. So we try to find how to reduce the energy consumptions of the batch arrow system and hybrid batch arrow system. So we believe that these configurations can be an effective solution to minimization of energy consumption. So this is the conclusions, and it's the pros and cons of each arrow configuration. Actually, continuous arrow system has simple implementation, and each scale up definitely it is appropriate to large scale desalination plant. However, the high energy consumption is a disadvantage of this continuous arrow system. About semi-batch arrow system, the smallest size of the system and high recovery achievable are the main advantage of the semi-batch arrow system. However, relatively high energy consumption should be considered when installing the semi-batch arrow system. About the batch arrow system, low energy consumption and high recovery achievability is the main advantage. However, the disadvantage is hard scale up to, especially in large scale system or over the full scale system. About the hybrid batch arrow, the low energy consumption, high recovery achievability, and operational flexibility are the main advantages. And over 90% recovery, then hybrid batch arrow system would be a better solution than the batch arrow system. However, the disadvantage is complex operation, and it is just in the step of the theoretical understanding, and we have to think about the validation and then installation of the pilot scale. It is the remaining topic of the researches. Okay, thank you for understanding. Thank you for listening for my presentation.
Okay, thank you, Dr. Park. A very interesting talk. You have given us a novel insight in the energy consumption and in different RO systems. Now I have a question. What do you think the main obstacle of the batch RO system for the scale up process?
This is definitely okay. This is because in the scale of operation, then the batch arrow system, the large scale pump should split the feed line into each batch arrow system, but the capacity of the freshwater production is limited by the size of the RO module. Actually, in continuous RO system, the series configuration can be overcome the size of the limitation of the capacity, but in batch RO system, the series configuration is not effective in this system. So we have to think about the installation of parallel system, but we have to think about this is the main obstacle to realize the large scale system over full scale system.
Okay, thank you, Dr. Park. Thank you again.
Thank you.
Okay. Now the section 5A is coming to the end. Thank you again to all the speakers, Professor Tang and other four speakers, as well as thanks all the audience to the careful listening. Okay.
Thank you. Thank you very much.
Thank you very much.
Thank you. Thank you, Professor Tang, and thank you, Dr. Du and Dr. Park.
Professor Xiong. Okay. Okay, bye-bye. So we'll end this session, right?
Yeah.